Trying. Oh, hey, here we go. It's Tuesday the 13th. Good afternoon, everybody. This particular week, we're up to chapter 7 for sure. You guys hopefully have been in there for a little bit. And chapter 7 is sort of where it all comes together. Where the design of the various systems. So normally this chapter is where people start to feel a little bit overwhelmed, a little bit confused. So if you're feeling that, don't feel bad. That's normal. If you're not, then feel smug and superior and all those other good things, right? Okay, so a couple of things in this chapter kind of want to highlight here, and maybe I'll jump in. I was hoping we had some real world numbers. I think, Brian, didn't you say you were going to get a copy of your electric bill or something like that we can use?
I can.
Okay.
I'll be right back.
All right. Sure, that'll be good. Yeah, what we want to do first, typically, when you get ready to do your installation, you've already gone through the site evaluation, and now you need to start figuring out how many panels you're going to need in the array, what's going to be the configuration of this array. When we say the configuration, like how many strings, how many panels in a string, that kind of thing. And usually the two things that you figure first when you're talking about selecting product is the panels and the inverter. So those are the two areas that you got to kind of focus in on first. The rest of it you can all sort of usually figure out as you go along, such as what kind of racking system you're going to use, what are your disconnects going to look like, combiner boxes, junction boxes, that kind of thing. But the inverter and the panels are going to have to be sorted out relatively quickly.
Jay,
So
this is Ted.
yeah, hey Ted.
Hi. When you get to the PV watts calculator, I've got some questions on the system info, because that apparently is giving you the information in order to be able to determine the size of your array, the watts, things like that, the panel size, the string size.
Okay. Well, why don't we jump into that right now? Because so what's your question on using PV watts?
So in the text, all of the examples that you used, understand about where your location is. That's very clear that it's obviously going to your angle, your tilt, your azimuth, system losses. Those are all going to vary. Your module type is pretty clear too, and it changes if it's a ground mount or rooftop or whatever. But I noticed in all the calculations, you always kept the DC size to 4 kilowatts. And we never dealt really with the array type. We just assumed that it's whatever they gave us there. But when we actually do these assessments, designing the system, how do you come up with 4 or 6 or 2 or whatever, for instance, the DC size? Because we never changed those.
Right. Well, and PV watts kind of defaults to that, when you first pull it up. But you're right. It's a bit of a guessing game, at least the way I do it. I'm sure there's a better way of doing it, but let me jump into PV watts and I'll show you kind of what I tend to do. Let's see, where's my all right. I need to jump in here. Okay, do you guys see the PV watts screen there? All right. Are you guys seeing the PV watts screen?
Yes.
Yeah.
Okay, great. So let me, since Brian came back with his, we'll kind of use it for him. Okay, so Brian, what city you're located in?
Well, we're in Points, West Virginia, but I couldn't get the bill. Sorry.
Okay.
online and we have to get logged in. It's I thought we had a paper copy handy.
Okay, well, no problem. We'll just make up some numbers then. So here we're showing points West Virginia, and it's always kind of nice to make sure that they've found the place that you think they should have found. So here, for instance, I'm showing you're just south of Cumberland there. That sounds
Yes.
about right. Okay. So we're in the right spot. And then as you were just pointing out there, Ted, if we jump in here, it just tells us the system size is 4 kW. And that's kind of the default size, but we don't know that for sure. So what I normally would do is, of course, you take the bill that Brian has provided, but in this case, as per usual, the customer is slow giving you stuff, but then they want turnaround time to happen immediately. So it's like yeah, whatever. All right, so let's say that you're a typical home, and your home you use, we'll just say 850 kilowatt hours per month. And so we're going to say 850. And just to make this easy, we'll say that it's constant every single month. So I'll just take 850 times 12, and that gives me 10,200 kilowatt hours per year. All right. So then we've got to sort of go and change other items. I'm going to say that we're going to do a SolarEdge system on yours. And I know from my experience, SolarEdge is going to be about 10% inefficient for the system. So I'm going to put in system losses of 10%. It defaulted in at 14 something. That's just too high. So I'm modifying it. Now, let's also assume, do you want this to be a ground mounted system, Brian, or a rooftop mounted system?
Can we do one of those? It's like a carport where you put
Yeah, sure.
considered. Is that a rooftop then considered?
It would be a ground mounted, but you can see that here Open Rack is one of the systems. Then there's roof mount, 1-axis tracking, 1-axis backtracking, 2-axis tracking. So so what we're saying here is for most cases, you guys are going to either deal with Open Rack, which is going to be a ground mounted fixed system, or roof mounted. So let's assume, just for this problem, I'm going to put it on your roof. So we're going to put it on the roof. And so I picked roof mounted, and then we measure the angle of your roof, and we find that it's 17 degrees. And we also find that the azimuth of this particular building we're putting it on is 145 degrees. It's not perfectly due south. It's 35 degrees off south. Now, I'm just making these numbers up, but you would do this during the site evaluation. So now I'm going to go and I'm going to see how many kilowatts per year did this system provide? Well, it's providing 4,913. But we found from our assessment, we need 10,200. So I need to a little bit more than double that. So I'm going to come back here, and I already know it's going to be somewhere, let's say 8.2 kW as opposed to 4. So I'm going to plug in 8.2. Still a little bit too small if I want 10,200. It's pretty close though. Let's say 8.3, just to overproduce slightly. Well, that's right about on target. So an 8.3 kW array. So do you see,
Hey, Jay?
Ted? Yeah.
Okay, so the solar radiation and the AC and the solar radiation, those numbers did not change. Those are for this particular calculator, those don't change, but they affect the results of the output per year.
Right. They affect it,
Okay.
but and what I need to do is then size the array, because each panel is going to generate based on the location, the azimuth, the altitude. But how big a system do I need to get the cumulative generation I need over the course of the year. So if you're just looking for your insulation, you know, your number there, 4.35, it doesn't matter what size array you're dealing with.
Right.
It's going to give you that number.
But that number, well, that number based on the other data you put in the previous input screen is going to affect the 10,194 kilowatts per year.
Yeah.
The azimuth, the angle, things like that. That is, but 4.35 in the AC, the solar radiate insulation isn't going to change.
Right. And in fact, if let's assume we just went in here and got 4.35, then if I wanted to size the array, let me jump out of here and go to the whiteboard. So the way that you calculate is we would take the daily load. So how do we get to daily load? Well, right now we know that it's 850 kilowatt hours per month. We divide that by 30.5 days per month. And we get, I'll let somebody else do the calculations. What's 850 divided by 30.5?
The numbers are fading my old solar calculator.
Uh-huh. See, solar's no damn good. I already knew that. All right.
27.87.
27.87. 27.87. And that's going to be kilowatt hours per day. Now, I want to get this number from kilowatt hours per day to kilowatts. So I divide by hours per day. Well, we just looked at that PV watts and found that the hours of insolation per day is 4.35 hours per day. So what is 27.87 divided by 4.35?
6.41.
6.41?
6.4066. So 6.41
watts. All right. And then we need to derate it by efficiency. So 6.41 divided by 0.9.
7.12
7.12
kilowatts.
Yes, kilowatts. All right. So this is telling us 7.12 kilowatts, which is strange because it should have been 8.3, right? According to that other when we played around with it. 27.87. Let me just double check the math. 850 divided by 30.5. 27.87, yeah. 27.87 divided by 4.35. 6.4 divided by 0.9. 7.11. Yep. Okay. Well, all the math is right. The result is telling us that we should just need a 7.12 kW inverter. Or
I lost.
array.
Where did you say you needed 8 point something?
Well, remember when we were back on the PV watts page?
Yes.
Yeah, remember here, if I go into the share the screen, where's the PV watts? There we go. Here, it told me that in order to get 10.2, which is what I needed, I needed 8.3 here because of the angle and the tilt that I put in there. It may be, oh, it's adding, maybe it's adding in. Let me see what happens if I change that to 100%. It didn't like 100%.
Oh, it says between 0.90 and 0.95, didn't it?
Uh,
0.95, okay.
99%. Yeah. Okay. So let's see what happens here. Yeah, a little bit more. So it was adding in the 4%. So system losses 9. Let's see what 7.12.
1.2.
Still coming in pretty low. I just wonder why it's monthly irradiance loss, ground cover. Ground cover ratio should be that didn't matter. Okay, yeah, I need to understand why it's underperforming there. It's saying it could be up as far as 9.6. It's throwing in some additional losses somewhere. This shows a little loss calculator here. It's still throwing in 14% there. Maybe you've got to come in here and plug it in here. Now they keep changing stuff. Mismatch should be 0. Soiling 1, shading 0. Let's do that. That didn't do anything, did it?
Or less.
Yeah. Came in at 9.6. Nameplate rating. A little bit more. All right. I would go still, I'd come in here and I'd put the 8.2. As you can see, none of this is a real exact science, but the way that we figure it is it's coming in, if we're saying 850 kilowatt hours per month divided by 30.5 gives us the daily rate. Then you divide that by the hours of insolation, and then you divide that by the system D rate. So that's how you calculate the size of the array.
The other question I had about this calculator is if you're using a standalone system, because
Yeah.
of the other factors you might put in there, if it's a standalone system you're trying to design, does using PV watts assume you're not using a standard? I assume you're being grid
Yeah.
tied.
Yeah, it does. And I think right down here under advanced, you can plug in your monthly irradiation here, and that'll help adjust it, because you remember you've got to have sort of worst case month to this is always going to be basing the array size on averages, on annualized averages. But with a standalone system, you've got to have the worst month of production paired off with the consumption. And you get you figure out which month is the worst ratio between those two, and then you design the system for the worst month. So for instance, in February, you may produce the least amount of energy, but you might have the highest amount of electrical use. So you got to set your array up for that. But PV Watts assumes grid tied because more than 95% of all the systems out there are going to be grid tied.
Is there a separate kind of calculator NREL does for off grid?
No, I don't, not that I'm aware of anyway.
Okay.
my guess is you could just simply plug your radiation losses in here somehow and come up with something. But I think you probably just want to use what we've got in the book. Get your in fact, here, what you could do is you could size it instead of going with the 4.35, you would take these numbers, which are going to be
Yeah.
month by month irradiation.
And
then
that's regardless of whether the solar radiation column there is regardless of whether you're, regardless of what kind of PV array you're using.
Yeah, right,
Okay.
right. Yeah, they're just saying how much power is coming out of the panel. I don't
How
care
much-
if you're connected to the grid or how much light is hitting that panel, I should say.
Okay.
So those are 2.3 in December, 2.3 units of 1,000 watt, 2.3 hours of 1,000 watt power.
Mhm.
Yeah, so it is a little more confusing when you're having to build a standalone system, and certainly more expensive.
Yeah.
But
And we haven't even gotten to batteries, so that's a
Yeah,
later
yeah.
discussion.
Yeah, so you're so anyway, so that's kind of using that. And then as far as with the system there, let's say that we decided that you needed, I'm going to go with the 8.2 kW system. So under that scenario, we're going to say we've now determined we need an 8.2 kW system. So how many panels is that? Well, now we got to go out and buy a panel. We got to go and see which panel do we want to select. And it might be, for example, I'm going to share here and we'll go in and we'll just go to Alt-E. I just like the way their site navigates. And we'll go in and we'll buy some solar panels. And we'll look, and one of the reasons I like this site is because you can sort by price per watt. So I can sort it here. And now if I look down, their cheapest panel is a Hyperion 400 watt monocrystalline all black panel. So it's 34 cents a watt. That's pretty good retail. That's dirt cheap. I mean, $135 for a panel. So let's just say that we're going to go with this 400 watt panel. Well, then how many panels do we need? So we've determined it's an 8,200 watt array. So 8,200 divided by 400. And we need 20 and a half panels. So can't buy half a panel. So do we need 21 or do we need 20? And some of this is going to depend on the inverter we select, on the system we select, because let's say we go with a simple string inverter, then my assumption is going to be 20 panels. We're probably going to end up at 2 strings of 10 or 2 strings of 11. So do we want to go with 20 or do we want to go with 22? Well, I don't know, probably 20. That's a little closer to where we're at. So at this stage, now we got to look at buying an inverter. So before we move off of this panel, we've decided this is the panel we're going with. So I'm going to make a couple of notations as far as the system. I want to note down what is the ISC, what is the IMP. So here's the VMP is 31 volts. The VOC is 37.07 volts. The IMP is 12.9 amps. The ISC is 13.79 amps. And as we know, the IMP times the VMP should equal 400 in this case, just because of the IV curve. Now, I'm also going to need to know what's the temperature coefficient. Well, the temperature coefficient at VOC is 0.304% per degree Celsius. And the temperature coefficient at VMP is the same as at Pmax. Pmax is VMP times IMP. So the temperature coefficient there is going to be 0.36% per degree Celsius. All right, so I've made note of those. Now I'm going to go and I'm going to look at the inverter. And I need an inverter. It's grid tied system. I'm going to do a string inverter. So under this scenario here, they've got GoodWe, huh? I've never heard of those guys. So the GoodWe, I could go with this one. Let's just use that. Oh, it's APS. Okay. APS, good system. Very, very commonly used in utility scale for sure. All right, so let's pick this inverter. We're going to spend $1,275 of Brian's money here on this system. And I'm going to just pick that one just for the heck of it. All right. So we now know that its capacity is 8,600. Well, we set an 8,200 watt array. That's more than enough. I could have gone with a smaller one, maybe a 7,000, but they didn't have that. They had a 6, which seems a little too small. So now there are a couple of things I want to look at here in the spec sheet. One is, let's make sure, well, the maximum voltage input is 600 volts. The startup voltage is 150. So I need to know 150 volts startup, 600 volt max. And I'm also curious as to what is the efficiency. Well, the efficiency here, it looks like you lose about 2.5%. That was all built into our D rate. So, you know, when we were figuring out the calculations, we would have looked in here first. But inverters in today's market are going to be 2 to 3%, you know, pretty right across the board. So those are some of the issues that I want to know. I can also look up to see what is the output amperage here. Parent output power, does it give me an amps? Sometimes they're very helpful. They just tell you what the maximum output amperage is.
They have short circuit current.
Yeah. I don't see AC reverse. Yeah, there's that's per string coming in.
That's input. Okay.
Yeah. It's telling me that the output is 8,600. The nominal, maximum, no harmonic. Boy, we might have to go in and look at the spec sheet. Here, sometimes the spec sheets have more information. So the output, yeah. Here's, well, nominal apparent output power frequency 86. All right.
Jay, what is the VA? What is that? Is that voltage?
Volt amps.
Apparent volt amps?
Volt amps, yeah. And that's a little bit confusing because loads use power in terms of watts. But generators produce power in terms of volt amps. And of course, watts equals amps times volts. You know, so they're kind of, you would think they're the same thing, but they're not quite, because not every load uses power at 100%. Resistive loads do. So in a resistive load, like a toaster, for an example, it will receive, say, 100 volt-amps, and it will use 100 watts, and those things are equal. But a motor or an inductive load has the inefficiencies built into it. So in fact, it takes more power going in than the amount of power that's used. They always try and explain it like the foam on the head of a beer. You can't get the beer without the foam, in a draft beer, but you can't really drink the foam, although people do, obviously. So the analogy falls down. But anyway, it's there's reactive loads, inductive loads, and then you've got real power. And I'm losing the terms in my head. But anyway, volt-amps is basically a measurement of generation, and watts is a measurement of consumption, and they're not always the same thing. So
But it's an output.
generators,
So, but that's output though. So there's
Yeah.
no way using that volt-amp rating to back figure what the output
oh yeah,
amperage would be?
yeah, for sure, there is. In fact, in this case, 8600, I would just simply take 8600 divided by 240, because this is going to be a 240 volt system because it's tied to the grid. And that's just going to tell me that it's 35.83, or basically 36 amps.
And why did you need to know the output amperage you were looking for the
Well-
AC tie into the house?
Yeah, because now I'm going to try and take all this information and design the system. So I need to know what's the amperage going through those wires so I can size those wires.
Okay.
That was all. So normally you can just pull it off the spec sheet, but in this case, you're just not able to. All right. So
So 35 amps, just out of curiosity, what size wire would you use?
well, 35 amps in this case for that. Well, let's do the whole system before I get into that. All right. Oh, I'm using my pen on the whiteboard and I'm wondering why it's not moving around. All right. So let's just start over here, and we've decided we needed, we said an 8.2 kW array, and we're using 400 watt panels. So I ended up needing 20.5 panels. And now I need to come in and how many panels in a string? So in this case, how would we figure out the maximum number of panels in a string? Well, the first thing you got to do is you got to look up on the internet and say, what's the coldest day? What's the coldest temperature that site has ever experienced? So in this case, Brian, you're living there in the mountains, sort of, or in the valley. In your location, I could look it up, but well, we probably should look it up. So if I go in and say coldest day ever in Points, West Virginia. Where were the hottest and the coldest days? It probably is not going to give me the coldest in your particular city, but this one will tell me what's the coldest and the hottest, I think, in West Virginia.
I'd probably have to give you a bigger city. You wouldn't want to blink your eyes in Points or you'd miss it.
Well, they're saying that Death Valley, Alabama. Oh my, this is going all the way. West Virginia. All-time highest was in Moorfield. What do you know?
Oh, that's close.
Yeah, 112 degrees Fahrenheit. And the coldest day ever was in Lewisburg, minus 37. So we'll use those. but those are Fahrenheit. So then I've got to go, all right. Fahrenheit to Celsius. And the Fahrenheit for the coldest is minus 37. So minus 38. Minus 38 Celsius. And while we're in here, let's do 112 is 44.4 Celsius. All right. So now we're going to go into the whiteboard. All right, there we go. No. This thing decided to move it into the middle. All right, I'll work with it. All right, so how do we figure this? We take the coldest day ever, which is minus 38. We find the difference between it and standard test conditions. So the delta is, in this case, 38 plus 25 is 63, right? Is that the delta?
38 and 23, 61, right?
No, 38 and 25.
Oh, yeah, 63.
Yeah, 25 degrees Celsius is standard test conditions. So what's the difference between minus 38? So if we have a continuum here, and this is minus 38, and this is 0, and this is positive 25, then the difference between these is 63 degrees. Okay. I see, see these cursors jumping around. All right, so so we take that 63 degrees and we multiply it times the temperature coefficient at VOC. And the temperature coefficient at VOC was 0.304% per degree Celsius. So that was off of the panel spec. So now I take 63 times 0.304, and I get 19.15. So 19.15%. So on the coldest day ever, that panel is going to produce 19.15% more volts than it will under standard test conditions. So now I would find out, well, what is the VOC? Well, the VOC was 37.07 volts. And that's VOC. So then we multiply it times 119.15%. Everybody see why it's 100% plus 19 is 119%. And if we want to decimalize that, I would put 1.1915. So that just gets rid of the percentage, turns it into a decimal. So I now take 37.07 times 1.1915, and I get 44.17 volts. So on the coldest day ever, that panel might produce 44.17 volts. Well, what's the maximum voltage our inverter can handle? Well, from the spec sheet, it was 600 volts. So I divide 600 volts by 44.17 volts, and I get
13.58.
13.58.
Mhm.
All right. But I want to not exceed 600, so I round that down. So it's going to be 13 panels max. Everybody see how that works?
Mhm.
All right. Now I could figure out what the minimum is as well. In that case, I would find the delta between the hottest day ever. So in this case, that was 44.5 or 44.4, 25 degrees still. And now that's going to equal 19.4. Is that right?
4.
But we have to figure out if it's a ground mounted system, we add 25. If it's a rooftop ballasted system, we add 30 degrees. And if it's a flush to roof, we add 35 degrees because it's hotter on the roof. Well, we decided this is a flush to roof. So I'm going to add 35 degrees Celsius to that. So now we've got 54.4.
Mm-hmm.
So that's now our temperature delta. Well, now what we do is we take that 54.4 degrees Celsius times, and it's the temperature coefficient at VMP, which in this case is 0.36. And we get 54.4 times 0.36. 19.58. So on the hottest day, it's going to produce 19.58% less voltage. So, and less than what? Well, we're going to use VMP, not VOC, because we want to use not the worst case scenario, but the normal case. So we multiply that times 100% minus 19.58, or that's going to be 0.8042. So 80.42% decimalized. So what's 31 times 0.8042? I was thinking somebody had a calculator.
249.
How much?
249.3.
Probably 24.9.
I'm sorry, 24.9. Yeah.
31 times 0.8042. 24.9, yeah. So 24.9 volts. So on the hottest day, it's only going to produce 24.9 volts. Well, what do we worry about? In this case, we're worried about the startup voltage of the inverter. And from the spec sheet, that was 150 volts divided by 24.9 volts. So 150 divided by 24.9 is
6.02.
6.02. So minimum 6 panels. So a maximum of 13, a minimum of 6. Well, we've got 20.5. So clearly my assumption was right. We can either do 2 strings of 11 or 2 strings of 10 in this case, right? So let's go ahead and do 2 strings of 10. So now we're only going to have 20 panels, and 20 times 400 watt, pretty easy math. That's going to be a basic 8.0 kW system, right? So now we're coming into, let's say we're going into a combiner box. Well,
Hey, Jay?
yeah.
Okay, yeah, I know you had 20.5 panels in order to keep it below the 600 volt maximum, but what if you did 3 strings of 7?
We could do that. We could do that, but then you're really you're gonna lower your voltage, so that's gonna increase the effective voltage drop on your system. And you're also gonna have one more breaker, one more set of wires. You know, all of those things are gonna add to the cost. So
Okay.
I always try and push the voltage up as close or as high as possible. So you're just going to minimize your cost. If you're wanting more production, you could go with 22 panels and have 2 strings of 11. That's fine. A lot of these are guesstimates anyway. So you're kind of, yeah, but I wouldn't go with 3 strings of 7. That would just raise costs unnecessarily.
So,
Jay,
Go ahead, Josh, and then back to you,
um,
Ted.
sorry, I have a question about the temperature coefficient. Say you are going to be installing an array in an area that, like, for example, this one, where it can reach negative 30 degrees Fahrenheit. Um, if that area also experiences like high winds around that time of the year, would you need to try to factor in like an additional few degrees for wind chill or?
Oh, yeah, I could see that the logic is there, but nobody ever does.
Okay.
Yeah, I mean, it would,
Because that would
if,
lower the ambient temperature of
yeah,
the array.
yeah, it certainly, would feel like it would, unless of course it's sheltered.
Right. Yeah.
So I don't know. And probably during this time period, the bloody thing's covered with snow anyway, so it's not producing, so who knows, but
Okay.
all of this is kind of our best guess.
Gotcha. Fair enough.
Yep. The worst case is that it's going to over voltage it. It's going to send too many volts to the system and the inverter's just going to shut down.
True.
So they have protection for that. So,
Okay.
all right. So as far as size of wire, well, coming in here, we know that typically these things come with, in today's market, 12 gauge wire attached to the panel. So this PV source circuit here from the panel to the combiner box is probably going to be 12 gauge wire. Well, is that going to be adequate? Well, in this case, we're going to take the VOC, or no, sorry, we're going to take the amps. And in this case, the amps were, ISC was 13.79 amps. And we're going to multiply it times 1.25, which is the NEC safety margin. And because there are no electronics here, we're also going to multiply it times 1.25, which is the solar variability factor. So 13.79 times 1.25 times 1.25 gives me 21.54.
Mhm.
Did you guys get the same?
Yeah, 21.55 or something like that.
Yeah, okay. All right. So if we look up in the book, what size wire do we need? Well, it looks to me on these panels, my assumption of a 12 gauge wire is probably going to be wrong. It might be. I mean, it might be because 25 amps, the 12 gauge wire would still work. But it might be 30, it might be 10 gauge wire. If it is 10 gauge wire, we're fine. If it's 12 gauge wire, we're still fine because the maximum for that is going to be 25 amps. If you read it in column 1 and the table that's on page 104. All right, so the ampacity here is going to be 21.55 amps. All right, if I'm putting it into a combiner box, I'm going to leave with just one circuit. So I would take that number, it's 2 strings, so I'd multiply it times 2, and I'm going to be leaving with 43.1 amps. Do you see that? By combining them, I don't have to put the safety margins in again because they're already built into that number, but I'm combining 2 strings in parallel, so amps increase, but voltage remains the same. So looking at the same table there on page 104, I can see that I can't use 8 gauge wire because that's only rated to 40 amps. So I've got to use 6 gauge wire. So I'm going to come out of there 43 amps. Right? 6 gauge wire. 6 gauge wire is rated to 55 amps. So now I come to a DC disconnect. What size DC disconnect do I need? Well, DC disconnects typically come in 30 amp, 60 amp, 100 amp. Those are the main ones that we'll run into. So I don't want to use a 30 amp. because it's not going to be enough. So I'll use a 60 amp rated box. But if I have, say, a fuse or a breaker in here, what size breaker do I need?
It has to be below 60, right?
Yeah, it's got to be, well, it's got to be below 55 because the 6 gauge is 55 amp rated, and you're really protecting the wire. So
it's
this is only rated to 55 amps. So
So
you
50
round up to the next available size. So I'm going to put a 45 amp breaker in there, or a 45 amp fuse in there. It's got to be sure that it's less than the wire's capacity. Otherwise, the wire will just burst into flames. So we round up. So I'm going to put a 45 amp fuse in there. From here, does the wire change as we move forward?
shouldn't.
No, because it's just a disconnect, right?
Yeah.
So now the next piece of equipment that we're going to go to,
Inverter.
yeah, for a grid tied system, it's going to be an inverter. Well, we've already decided that the inverter that we're getting, it was a 8.6 kW inverter, right?
Mhm.
The wire here is also number 6. And does anything change inside the inverter as we leave? Do we just leave with number 6 wire?
DC.
I'd say no, because you're converting to AC then, right?
AC.
Yeah, it's converting to AC, and this is why I needed to know the amps. So in this case, I could take 8.6 kW. We know it's going to be 240 volts. So 8600 divided by 240, we ended up at 36 amps. And we take that times 1.25. We don't have to do the solar variability because we're on this side of an electronic device that's evening that out. But we still have the NEC safety margin. So 36 amps times 1.25.
44.8.
Yeah, 45 amps, more or less.
45 amps.
Yep. So 45 amps. Well, it just sort of turns out these things are going to be very similar. It's not always that way. Well, 45 amps, we already know from our table, we still need number 6 wire. Right?
Yes.
So now we're going to go to an AC disconnect. And the AC disconnect is going to be 3060 100 amp. So it's going to be a 60 amp box with a 45 amp breaker or fuse, right? And then from here, the AC disconnect, we're going to go into our service panel. Well, let's assume we've got 200 amp service. It's a 200 amp panel, 200 amp box. This is going out to the electric grid. So can I come in here with the load side connection? What size breaker would I need to connect to?
Uh, 320 amp breakers. I don't know.
No, it's
315 amp breakers.
It's going to be a double pole breaker. It's going to have to be a 45 amp breaker, right? Because we're bringing in 45 amps of service. We round up to the next breaker, just like we did the fuse here. Well, it turns out 45, 45, that's fine. I could come in with a 45 amp breaker, but I've got a problem. If I try and put a 45 amp breaker with 200 amp service from the utility in a 200 amp panel, I've exceeded the 120% rule. It tells me I can only go to 120% of the bus bar rating of the service panel. So it turns out with a 20 amp or 200 amp service panel, 20% is going to be 40 amps. And I'm trying to put a 45 amp breaker when I could only legally put 40 amps. Is that
That's
clear
the
to
biggest
everybody?
breaker you can, that's so 40 amps is the biggest breaker you can put in that service panel because of the safety rating.
Yeah, because I'm exceeding the bus bar by 120%. So now
Wow.
I've got a couple of choices. Well, one choice, and you're seeing this increasingly, oftentimes these panels, these service panels are rated for 225 amps, not 200 amps. Well, what's 20% of a 225 amp
45.
45? So I'm
That's
cool.
all.
If that were the case, if it was a 225 amp rated panel, I'm fine. Or if it's still a 200 amp panel, what I could do is I could replace this breaker here, the main breaker, and I could put in like a 175 amp main breaker from the utility. And then I'd still be fine because it's the combination of the two that cannot exceed 120%.
So you got 25 then because to add to your other side then to your
Yeah.
panel side.
Yeah, so I could go as high as 65 amps down here if I reduce this breaker to set 175. So it's the combination of the two. So the only downside of that is that, let's say at night when my array is not generating, I'm now limiting myself to 175 amps versus 200 amps. Probably not a problem in most homes, unless you do a lot of midnight welding or something like that, you know.
Or you have
So
a garage workshop that has table saws and other high amperage stuff, and you're
yeah,
using a microwave and a stove at the same time, and
yeah,
running
but
your laundry.
it would have to be after dark. It'd have to be when the array is not producing, because you're still getting the production from the array, you know. So if you're doing it during the day, you're not in trouble, you know, unless the panels are covered with snow. So that's a decision you're going to have to make. Most people don't push the limit for their utility. You know, if you've got 200 amp service, you're probably not drawing anywhere close to 200 amps at any particular time. So that's probably a solution. But the downside is you've got to somehow disconnect from the utility to swap out that breaker. So you're going to have to contact your utility or have an electrician come in and make that change. Whereas if you're under the limit, you can just turn off the breaker and put your connection in and then just turn the breaker back on and everything's fine. So this is a more expensive process because you've got to disconnect from the utility to do it safely.
Okay.
Yeah.
So if you went ahead and did your analysis, and let's say your load said your load analysis said you needed all that energy in your structure. Sounds like it's a home and a business in the same structure. And you had only a 200 amp panel. That would you call your utility and say, hey, I need more service, another 200 amp panel or something like that? If you really had to have your 8.2 or 8.6 kW or 8,000 or 8 kilowatts of demand.
Yeah. I mean, under this scenario, you're still going to get that power. The question is when you're using the power in this scenario. You know, you're by adding the solar array, you're actually using less power from the utility than you are before you use the array or before you add the array. But are you saying, I mean, you could swap out the service panel for sure. You could put in a more robust service panel and then it's not an issue. You know, I could put in a 400 amp service panel and not change the 200 amp service from the utility. And then I've got lots of capacity. What we're
Okay.
talking about is the bus bar rating of this
Right.
piece of equipment.
Okay.
But if you swap out a service panel, that's going to be a $2,500 job.
Mhm.
You know, and that's money you just as soon avoid spending. Because, you know, you're going to hire an electrician, they're going to come in, they're going to move all the wires, remove everything, disconnect and all of that. And that usually ends up costing about $2,500. So
I
if you can
realize that.
avoid it,
Yeah.
you want to. Another option would be don't do a load side connection at all. Simply come up here and connect in somewhere between the meter and the main. Then you don't have a problem here at all. That just remains as it is. And now we're just feeding into a supply side connection.
You'd still have to have the power company disconnect, right? To put.
Oh, for sure.
If you're
It's-
wiring into an existing system.
Yeah, and you're going to have an electrician come and cut the wire somewhere and put a junction box in here with a bus bar connection type port and all of that. So supply side connections are even more expensive than just swapping out the breaker.
But that would be ideal if you're building a brand new house.
Oh yeah, in fact, you know what the best solution is and where we're moving to is all new electricity, all new systems are required here at the meter to have a main utility disconnect right there at the meter. So you don't even go into your service panel anymore. And most of these have a couple of places for double pole breakers. So it's like a mini service panel right outside, right at your meter. So in a case like this, you don't even have to go into the house. I could just come from my AC disconnect and then just connect right in here to one of these double pole breakers. And we should be fine.
And then that bypasses the meter still.
It's on the load side of the meter.
Right.
So it still works. It's ideal, for example, for a gonna clear. How do I get to another? Yeah, if I want to get to another, add a page. There we are. Yeah. So what often happens is, let's say you've got your home here.
We still have the old screen.
Oh, you're still on the old screen?
Yeah.
Let's see. How do I?
Go back to you and reshare.
Okay.
When I was in school, we just used an eraser.
Yeah. Let's try I'll just do a new whiteboard. All right. So let's say that you've just got a roof here. And you've got your solar array up here and you're using microinverters. Well, what's really nice is all of the microinverters are already here. We could just simply come down the side of the building,
Mm-hmm.
come to an AC disconnect, and then just go right into the meter box and never penetrate the house at all. You know, we never even have to come inside, which is great. So that, you know, everything is monitored out here. Everything's outside of the building. So those meter boxes now, those utility disconnects are required as part of the 2023 NEC. So if you do a substantial electrical upgrade, your utility might say, "Hey, you gotta put in a new meter box," because, you know, every time you do a substantial change, you've got to get it up to code, and that's going to be the new code. So All right, so we're out of time on this particular one, but I think maybe for next well, we're gonna have to I know I've got some off-grid videos as part of the review. If you want to look at how you size for that, how you size the battery banks and all of that. We'll try and finish that up if we have time next week. Next week's the last one of these sessions before we get together. So so then we're going to be a little bit pressed for time, but there are a lot of those videos that you can review on that list if you have the time and energy. Any questions before we adjourn here?
We just have one more Solar Tuesday, and then we meet up in Moorfield, right?
Yeah. Yeah.
Okay.
Gotcha.
I'll
Yeah,
be
I
missing
think
in action next week.
Yeah, let me just double check my calendar because I'm showing.
I think that's right,
Uh,
Jay.
Yeah. Yeah. So yeah, we do next
The 20th, I think, is the next call, and then the 28th and 29th to meet at the college.
Yeah.
28th and 29th. Yep. Yep.
Okay.
So and of course you guys can contact me throughout the week too if you have a question. You don't have to wait until the Tuesday. So I know some of you have sent me notes and hopefully you got the right answer.
Do you
via
have the
email.
address? The address for Moorfield?
Let's see.
Brian, I can send it to you if you want me to.
Yeah, that'd be great.
Yeah, it's pretty.
It's 316 Eastern Drive, Moorfield, West Virginia, 26836.
Just 316 Eastern Drive.
Yep, 316 Eastern Drive, Moorfield, WV, 26836.
I suspect it's pretty much the only building on Eastern Drive. So
Yeah,
Jay,
you can see
that's
it. You can't miss it.
Yeah, I figured
it's a big building and a big parking lot. Where do you have a particular location? Are we meeting on the side of the building or right inside somewhere?
no,
in the room?
you'll go in the main entrance and then we're on the second floor. The whole campus is really just one building there, unless you're going to the Wynn building, which is away from there. So yeah, we'll meet up on the second floor. I forget the room number, but I'll send that
Is it
to you.
204?
204.
I want to say that's right. I could be wrong, but I think it's 204.
We'll probably end up meeting at the front door because every time I've done this before, they haven't unlocked the door and I've got to stand out there and bang on it and, say, hey, somebody let us in. So
And what time are we supposed to be there? 8 o'clock?
8 o'clock. Yeah.
Jay, I've got my key card, so if I get there whenever you do, I can open the doors for us.
Okay. Terrific.
Wonderful.
All
Yeah.
right.
Sounds sneaky.
Sounds sneaky.
That's right. Okay. All right. I
Thank
think that's it. So
Thanks,
I'll
Jay.
talk to you guys next Tuesday. And if you have any questions, just send me an email.
Thanks.
Awesome.
All right,
Take
take
care.
Bye-bye.